Section 5.2 Basic Probability Rules. Let's say we want to explore probabilities that result from rolling two fair six-sided dice, one that's red and one that's blue. How would we develop a probability model for this chance process? So a probability model is going to show us everything that can happen along with how likely they are. And the first thing when it comes to creating a probability model is to define the sample space. So sample space shows all the results, all the actual outcomes for events. So when we roll these two dice, we can get anything from a 1 through a 6 on the red dice, anything from a 1 through a 6 on the blue dice. Okay, so as you can see, there's 36 different outcomes here. All of them are equally likely. Okay, we also can put it into a table like this if we don't care which color each die ends. And we only care about what the sum of those are. So for example, this result and this result aren't any different if we're just looking at the totals. So before we get into some actual problems, here's some key terminology that's going to come up again and again in this chapter. A probability model is anything that describes all the possible outcomes for some situation along with their corresponding probabilities. All of those outcomes together are called the sample space. That just tells us everything that can happen. And one other key term is an event, which is just any collection of outcomes from our situation. So let's say we want to find the probability of event A, which we're defining as getting a sum of 5 when we roll these two six-sided dice. When we talk about events, we usually define them as capital letters. And we would write it as P with A inside parentheses, or we could actually just write what we're finding. So find the probability, that's what that P means, that we get a sum of 5, or that we satisfy event A, which is defined up here. So there's a number of different ways that we can get a 5. All right, we can get a 1 and a 4, we can get a 2 and a 3, all right, with the red die having the smaller number, or vice versa, where the blue die has the smaller number. All right, so there are 4 total outcomes in this event, event A, and that's out of the 36 possible outcomes that were displayed in that table of all the different dice. So the probability of getting a sum of 5 would be 4 out of 36, or 0.111. When it comes to calculating probabilities for equally likely outcomes, it's just a simple fraction. In the bottom, we're going to put the total number of outcomes, all right, which was that table showing all the different ways that we can roll 2 dice and the 36 outcomes that would result from that. So there's 36 total outcomes on the bottom. And then on the top of the numerator, we just put the number of outcomes in whatever event we're looking for. Now let's say we flip a fair coin 3 times. We want to write out the sample space, which are all the outcomes that can occur, and it would look like this. When it comes to figuring out what outcomes are in our sample space, it can be a little tricky, and the easiest way to do it is with a tree diagram. So we flip our first coin, and we get either a heads or a tails. After that, we flip our second coin. Again, we're going to get a heads or a tails. Okay, same thing down here, heads, tails. And then we flip our third coin. Heads, tails. Okay, now the sample space is just going to be all of these outcomes combined. I'm going to stop writing these now. But for example, this one right here comes from heads, heads, heads. Okay, this next one, heads, we're still on this top branch, and we're going to go, instead of this top one up here, all right, to that second branch. So we started off by going just all 3 across the top. Next one we go top, top, and then branch off to that bottom one. All right, and then for this next one we go top, tails this time, heads, that's that one, tails, etc. All right, so that's the tricky part, figuring out what is the actual sample space. Once we have that, the rest is easy. All right, in part B it says if event A is defined as getting exactly 2 heads, find the probability of A. Well, this has exactly 2 heads, this has exactly 2 heads, and this one has exactly 2 heads, which is 3 out of 8. We're going to see a lot of M&M problems in this probability chapter. Here we have the color distribution of M&Ms produced in the Cleveland M&M factory. We're first asked to explain why this probability model is valid. It's a valid probability model as long as it abides by those two rules. So number one, we need valid probabilities, which is the case here because all of these probabilities are between 0 and 1. And next, we want to just make sure all of those add up to 1, which is the case here. Next, find the probability that we don't get a blue M&M. So there's two different ways to do this. So to start, we could just add up all these probabilities that are not blue. Okay, but easier than that, we can just take the probability that it is blue and subtract that from 1. That's less for us to punch into our calculator, less opportunities for us to make a mistake. We get 0.793. What's the probability that we get a green or a red M&M? In this probability chapter, anytime we see this word or, it means we're adding two different outcomes together. So we can get a green one, or we could get a red one. The probability of either of those occurring is their combined probability is 32.9%. Now we can only do it this way because these outcomes are called mutually exclusive or disjoint. That means they don't have any outcomes in common. If we pick a single M&M, it can be green or it could be red or some other color, but it's not possible to pick an M&M that's both green and red. All right, so again, that's called disjoint or mutually exclusive. There's no overlap if we were to make a Venn diagram of green and red. They don't overlap at all. So that process is called the addition rule for mutually exclusive events. So as long as we have events that are disjoint or mutually exclusive, again, meaning that they can't occur at the same time, we can just add those probabilities together. So to wrap out this section, we have the probability model for the 2019 AP Statistics scores. We're going to randomly select a student who took this exam. And in part A, we want to find the probability that the chosen student scored less than a 3. So in this case, they could have scored a 1 or a 2, or meaning addition. So we're just going to add those two probabilities together, and we get 0.408. In part B, find the probability that the chosen student earned a passing score, a 3, a 4, or a 5. We can do the same thing here and just add those up. But note, this is also a complement problem. Okay, and a lot of times these get easier if we know how to identify complements. So this event is the complement of what we just found. All right, it's everything where they didn't get a 1 or a 2. So we can just take that probability that we just found and subtract it from 1 to get 0.592. And note that's the same probability if we were to just add those three probabilities together.